Hi, my name is Charles Kaplan. I'm a professor at the State University of New York at Old Westbury, and this particular video is on integration by substitution. Now, let me show you what's going on. Here's a simple basic integration problem, x cubed plus 2dx. And if we go to integrate it, we just use the power rule. We have x to the fourth over 4 plus 2x, and we can rewrite this as 1/4 x to the fourth plus 2x plus c plus our constant. We can't forget that. It's incredibly important. Okay, now that's fine as far as an example like this goes. However, it won't work for something like this, where you see something that if we were going to differentiate it, we'd be differentiating it with the chain rule. So we need a different tool in our mathematical toolbox, and that particular tool in this instance is called integration by substitution. Now, we see that we have a 2dx sitting out here, and in particular it's the 2 that I'm interested in, and we see that if we were to differentiate 1 minus 2x, the derivative of 1 minus 2x is 2. So that's what we're looking for. And in this case, we have 2. The derivative of 1 minus 2x is negative 2. So we can make this work for us. Even though the derivative is negative 2 and we have a 2 out here, we can make an adjustment for that. So let's get to it. We're going to let u equal 1 minus 2x, and if we differentiate that, du is equal to negative 2 dx. We have negative 2 dx here and a 2 dx sitting on top. We're going to have to make a little adjustment here, and if we pull the negative sign out and move it over to the left, we have negative du is equal to 2 dx. Okay, so let's go back and integrate using u as 1 minus 2x. So we have the integral of u to the fourth, and we have a 2 dx sitting here, and we have a 2 dx sitting up here. So 2 dx is equal to negative du. Let's put that in here. Now we have just a negative 1 here, which we can pull to the outside of the integral. So we have the negative of u to the fourth du, and we can go ahead and integrate this using the power rule. So we have negative times u to the fifth over 5 plus c, which gives us negative 1/5 u to the fifth plus c. And let's make our back substitution now. Negative 1 over 5 times 1 minus 2x to the fifth plus c. There's our integral. Let's look at another example. We have the integral of 2x times x squared minus 9 to the fourth dx. Well, let's rewrite this and put the 2x next to the dx, and we see that we have x squared minus 9 to the fourth 2x dx. And lo and behold, and it's no surprise because these problems are set up this way, the derivative of x squared minus 9 happens to be 2x. So let's let u equal x squared minus 9, and therefore du is equal to 2x dx, and that 2x dx is what we have sitting right over in the integrand. So let's substitute u for x squared minus 9 in the integral, and we have u to the fourth, and we see that 2x dx, which is what we have up top here, is equal to du. So we can go ahead and make that substitution. So now it's just a matter of integrating. So we have u to the 5th over 5 plus c, just like you've been doing all along, which turns out to be 1/5 u to the 5th plus c. And we can back substitute now. 1/5 times x squared minus 9 to the 5th plus c. There's our integral. And we can check this easy enough. That's one of the beautiful things about integration. And let's do it now. We're going to differentiate this thing. Let me pull this down. Let's see, we had d dx 1/5 times x squared minus 9 to the 5th plus c. You don't really need to write in the plus c. I do it just out of habit, because when we differentiate a constant, it becomes 0 and goes out anyway. So, okay, so let's use the chain rule to differentiate this. 5 times 1/5 is 1, times x squared minus 9 to the 4th, right? We subtract 1 from the exponent. We multiply by the derivative of the inside term, which is 2x. So there's what we started with, I believe. 2x times x squared minus 9 to the 4th. So it checks. Everything is good. Okay, let's move on to the next example. We have negative 2x times the square root of 9 minus x squared dx. Well, we see, let's rewrite this, and we see that we have 9 minus x squared, and then we have negative 2x dx. If we look under the radical, we see that the derivative of 9 minus x squared is negative 2x, and lo and behold, that's what we have out here. So let's let u equal 9 minus x squared. Therefore, du is going to be equal to negative 2x dx. And we see that this negative 2x dx is hanging out here to the right side. So we're okay. Now we're going to rewrite this square root, but let's rewrite it with an exponent as with a fractional exponent as opposed to the radical. So we have the integral of 9 minus x squared to the 1/2 negative 2x dx. And now let's make our u substitution. It's the integral of u to the 1/2, and negative 2x dx is equal to du. So let's write du in there. And now we're ready to go. U to the 1/2 is u to the 3/2 divided by 3/2 plus c. We're adding 1 to the exponent. 1 is equal to 2 over 2. So 1 over 2 plus 2 over 2 is 3 over 2, and we divide by the same amount. Whoops, sorry about that. And to deal with the compound fraction, we invert and multiply. So we've got 2/3 u to the 3/2 plus c. And if we back substitute, it becomes 2/3 times 9 minus x squared to the 3/2 plus c. There's our integral. And once again, we can check this. So let's rewrite this. 2/3 times 9 minus x squared to the 3/2 plus c, and we're going to differentiate this. Okay. So let's differentiate this chain rule problem. 3/2 times 2/3 is 6/6, so that's 1 times 9 minus x squared. 3/2 minus 2/2 is 1/2 times the derivative of the inner portion, which is times negative 2x. The c goes out, it's constant. So this becomes negative 2x times the square root of 9 minus x squared. And I think if you look here, you'll see negative 2x times 9 minus x squared. That's what we've got here. It checks. We're good. We did it correctly. Okay. Well, let's leave it at that on this video. I'll have perhaps 6 or 7, maybe 8 more videos on integration by substitution. If you found this video helpful, I'd appreciate it if you leave some nice positive comments. In the meantime, then, I wish you all good health, good happiness, long lives, and a lot of luck. This is Charlie Kaplan saying goodbye.